Hi, and welcome to this recording on experimental error, which is the fourth little topic in our first unit of data presentation and interpretation. In this lesson, students will be able to quantify the error in an experiment and state whether it is acceptable. We're going to achieve this by calculating the absolute error of an experiment, calculating the relative error of an experiment, and then being able to evaluate whether the margin of error is acceptable for an experiment or not. Error is incredibly important in maths, engineering, and science. It can determine whether test or study is invalid or acceptable all on its own. Let's look at an example. So, two measurements of body temperature are taken before and after a drug is administered. The two results are 38.2 degrees Celsius, and the second one is 38.4 degrees Celsius. This shows an increase in the temperature due to the drug, does it not? It seems quite obvious. Well, first thing we need to consider is, well, if there is error, where could the error be coming from? So not necessarily those two things showing increased. Error could be caused by instrument calibration. So the two instruments could have been decalibrated between the two measurements, or we could have used two different thermometers or measuring instruments to measure the two things, and they both may have not been calibrated correctly. We could have been some human error, so could have misread the scale, or more likely, if they were using a non-digital scale, so an analog scale, or where you would read off a ruler or a thermometer or otherwise, you may have not been at eye level and you may have misread the reading of the thermometer a little bit. Or it could have been experimental conditions, so things like the temperature of the room changed, the temperature of the surrounding area. It could have been left out too long and affected and not have been in a controlled environment. All of these things could have happened. For instance, if we had found that the margin of error was plus or minus 0.01 degrees Celsius, then that's probably not significant in any kind of way, shape, or form. However, if we found the margin of error to be plus or minus 0.5 or half a whole degree, then it's very much significant, because it actually might show that there's a massive drop in the temperature rather than an increase. We need to quantify these errors before we make judgments as to whether they are acceptable or not. So for the types of error that we're going to talk about, we're going to assume that the apparatus has been checked and is used correctly. And we're going to start with absolute error. We're going to calculate the absolute error of an experiment. An absolute error tells you the range of values that a possible measurement could have had. So it's linked to the maximum possible error of the instrument, and is usually linked to the scale of it, as you'll see. To be able to calculate the absolute error is equal to plus or minus half the smallest measurable unit. And we'll look at an example where this is the case. Here we have a ruler measuring the extension of a spring. How accurately can you read the extension of the spring? Ask yourself. You should see that on our scale on our ruler here, the gap between here and here is 1 centimeter, and the subsequent gap that follows on from there is 1 centimeter, etc., etc. So the smallest measurement that we can make of this ruler is 1 centimeter. And if we consider that the absolute error is half at the smallest measurable unit, well, then the absolute error must be half of 1 centimeter, which is 0.5 centimeters, or 5 mil, depending on what way you think of your measurements. So what's the smallest measurement the measurement could be? Well, it could be 0.5 centimeters less than what you read it to be, and the largest it could be 0.7 centimeters more than what you originally read. If you read the original measurement to be 6, for instance, then the smallest measurement would be 5.5, and the biggest measurement would be 6.5. Let's look at another example, this one being the Empire State Building, which measures apparently 443 meters, an awful lot taller than Big Ben that's shown there. If I was looking to see what the absolute error for this would be, I'd look at the measurement. I can see that it's measured to the nearest 1 meter here, and so the absolute error would be half of 1 meter, or 0.5 meters. So the range of values it could have would be half a meter lower, which is 442.5. That means that 443.999999, etc., 442.49999, etc., would be just below it, so below the range of values, and it would go up to half a centimeter more, 443.5, that way. We sometimes call these things either side the limits of accuracy. So the range of values that the height could take are greater than or equal to 442.5 up to 443.5. One more example, and that's the Bugatti Veyron. 4.6 meters long, measured correct to 1 decimal place, so we can define it in terms of our accuracy of a reading at the time, so for 1 decimal place. So if I wanted to say the absolute error here, well, it's measured to 0.1 of a meter, so half of 0.1 is 0.05. And so our limits would be 0.05 less than 4.60, which is 4.55, and up to 4.65. And that is absolute error. We sometimes call the range of values between the upper and lower bounds, it's sometimes called the rounding error. And the length is measured between 4.55 and 4.65. So time to test yourself. In class, I would have brought in some measuring apparatus, some that we were familiar with, pipettes and measuring cylinders, etc. But for the moment, on the table below, you can add on the smallest unit of measurement for each apparatus, and then define the error for each piece. So I have 4 measurements on the left here. You can see the furthest that they have been measured to. You can define the absolute error and then put in the smallest possible value and the largest possible value. And with that, you should be confident that you can calculate the absolute error of an experiment. Let's see if you can answer this one where the numbers are a bit bigger. The Earth currently has a population of 7.1 billion to 1 decimal place. What's the highest score possible measure, or the highest possible measure for the population? And you can start to ask yourself already, well, is this a problem? Is it significant? And more importantly, is there a way to tell whether it's significant or not? Well, if you look at it, the measurement has been done to 1 decimal place, so 0.1 billion, which, if you know your billions or measurements well, you'll know that that's 100 million. And so half of 100 million is 50 million, or 0.05 billion. Once we've calculated that absolute error, it can be useful to calculate whether the error is significant. So we are going to use a measure called relative error, and it's our second learning objective, where we calculate the relative error of an experiment. Relative error is the calculation that tells us the proportion of the original number that is error. And this portion of mathematics that we generally use for comparing proportions is percentages. So while relative error can be measured by taking the value for your absolute error and dividing it by your original measurement, or comparing it to the original measurement, we more usefully look at the relative percentage error, where we do that same calculation of absolute error divided by original measurement and multiply it by 100. And again, let's look at the experiment with the spring. So for the measurement of the extension of the spring from before, let's say again our original measurement was 6 centimeters. Our absolute error from before was half a centimeter, because it's half of 1 centimeter, which is the smallest measurement we could make. And if we use our formula of the relative percentage error being the absolute error divided by the original measurement multiplied by 100, well, you should see that our absolute error is 0.5. Our original measurement was 6, and if you do 0.5 divided by 6 multiply by 100, you should get that that percentage is 30, and our relative error is 30%. Again, some more for you to test. Now, unlike beforehand, where I got you to look at the units of measurements, I'm going to pick some other arbitrary ones on the right here. So these values for the 0.5, 5, 20, 0.05 are actually the absolute error that you're going to put there. That's why I've kind of blanked it in, but if you want to see what the absolute error is, you can certainly put it in that column. I can get you to find the smallest possible value and the largest possible value, just like we did beforehand. But more importantly, I'm going to get you to calculate the absolute error. And remember that the absolute error, or the absolute error divided by the original measurement multiplied by 100, will give us our relative percentage error. And you can stick it in as a percentage. And if you do, you can stick your little title of this bit to include percentage in it as well. Or you can leave it as a decimal value. And if you can do that, you can consider that the calculation of an absolute error of an experiment is also done. The last objective that we had in this lesson was to evaluate whether the margin of error is acceptable for a measurement or not. And this is where things get slightly interesting and where your job as a scientist or otherwise really comes into play. We look at this topic further on in a unit called confidence limits, but really it is up to yourself to decide whether the relative error is significant or not. It depends on the use or the experiment that you're doing. For instance, if you're testing the drug for side effects like we did in the very first part, then that would be pretty important. If you're testing whether cats like certain types of food, it would depend maybe on how much you like the cat. But maybe again, because it's a life or death experiment, may be quite important. It is up to you to determine or reason whether the error is acceptable or not. As usual, we're going to look at some examples. But the thing to look out for is that the smaller the relative error, the more reliable the measurement will be. Just how reliable will be up for your interpretation. We will go back to our example of the spring. Our measurement was 6 centimeters beforehand. Our absolute error was 0.5. Our relative error in that case was 30%. Is 30% significant? I mean, you can decide for yourself if you want, but I would suggest that 30% is a significant error, no matter how you look at it. However, if our extension was 60 centimeters instead of 6, then the absolute error doesn't change, but we would do 0.5 divided by 60 multiplied by 100, and the relative error in that case would become 3%. And you could ask yourself, well, is 3% significant? And that one's a bit more open for conversation, because ultimately we wouldn't like any error, but our scale only lets us measure so much, and maybe 3% is pretty good, all being told. In general, the absolute error is not a good measure to use to define significance. We should use the relative error, but I would suggest straight off the bat that any error more than 10% could definitely be considered significant in any way, shape, or form. If we go back to our original question of the Earth, where we had the population of the Earth be 7.1 billion, and we found that our relative error was 0.05. Well, it seemed like 50 billion was a lot to start off with, but it turns out that that's a relative error of 0.704. Is that significant? It depends on the use of the data. Absolutely it does, but I would suggest that it's probably not. If, however, it turned out that we had done it to the nearest billion, and the population was 7 billion, and our relative error was 0.5, then that might give a relative error of 7%, and that is certainly on the borders of significant. What I want you to do is use the examples here with the previous example to suggest whether the error is significant. So I've given you 3 scenarios in which we're going to use this data, and you can decide whether it's significant. A figure to be used in a school project, would it be a significant error in that case? Would it be a significant error if you calculate future food consumption, or we're using that figure to calculate future food consumption in the world. So for planning purposes, would that be a problem? That 7% value. Would it be a problem in calculating the density of population per area for our housing requirements? Well, I'll give you a hint this last one. It turns out that I put that one in there because we actually don't have enough information and therefore is irrelevant for that use. I could have used a more obtuse example, something like the number of cats in the world or otherwise there. But you still have to decide whether your reading actually is relevant at all before you decide whether it's significant. And that should be calculating the significance of error in an experiment done as well. So hopefully by the end of this lesson, you feel that you can calculate the absolute error, you can calculate the relative error, and that you can at least make a discussion or an evaluation whether the margin of an error is acceptable for an experiment. Thank you very much for watching, and I'll catch you next time. Bye.